We are going to go over common logarithms, okay? So you have seen, we're quiet now. You have seen that the base 10 logarithm function, y equals log base 10 of x, is used in many applications. So base 10 logarithms are called common logarithms. So a common logarithm has a base of 10. So it looks like this one right here. So common logarithms are usually written without the subscript 10. So it is written more like this. So just log x. Okay, so that's your common logarithm. So most scientific calculators have a log key for evaluating common logarithms. Okay, so you can use that log key, which is on your calculator. Okay, for this one, this type of calculator here, that log button is right here, where it says log on your calculator. So you would press that button and it'd pop up as log in a parenthesis. That parenthesis is where you'd enter whatever number it is you're trying to evaluate. Okay? So that's what we're going to do in A and B right here. So we're going to round to the nearest 10,000th. Okay, to the nearest 10,000th. That is 4 decimal places to the right. So that would be like 0, 0, 0, 1. Okay, that is your 10,000th place value. So to 4 places there. So for letter A, we want to find log of 5. So on your calculator, you're going to press your log button. Okay, and then we want to press 5 to find log of 5. Okay, and then we want to round to the nearest 10,000. So this one would be 0.6990. Okay, because we have this 8, 9, and then a 7. Okay, that 7th one rounds this one up. That makes that one 10. So this one then turns to 9, and that one turns to a 0. Okay, so that would be your 10,000th place value. Okay, next one, enter log of 0.3 into your calculator. Log of 0.3. It is negative. And you should get negative 0.5229. Again, rounding to that 10,000th place value. Okay, questions how to enter that in your calculator? Awesome. So, the common logarithms of numbers that differ by integral powers of 10 are closely related. Remember that a logarithm is an exponent. Okay, it's the inverse of your exponential. For example, in the equation y equals log of x, y is the power to which 10 is raised to obtain the value of x. So if I have log of x equals y, that means if I were to bring in base 10, these ones would cancel out and you would have x equals 10 to the y power. Okay, so that's what they got here. Okay, if I had log of 1 equals 0, that's because 10 to the 0 power is 1. Okay, and so on and so forth. Okay, so 10 to the first is 10. So that's why we have log of 10 equals 1. What?
10 to the 111.
10 to the 111.
Right here.
This is an M. Alright, so common logarithms are used in the measurement of sound. So soft recorded music is about 36 decibels. Okay, so that's dB. So the loudness L in decibels of a sound is L is equal to 10 log of I over M, where I is the intensity of sound. Okay, I is the intensity of sound, and M is the minimum intensity of sound, detectable by the human ear. So residents living several miles from a concert venue. You can hear the music at an intensity of 66.6 decibels. How many times the minimum intensity of sound detectable by the human ear was this sound, if M is defined as 1? So we're going to use this equation here. Okay, so we're using the equation L is equal to 10 log of I over M. Now, M is defined as 1. Move up here. M is defined as 1. That's an L. This is an L too for log. Okay, we have an intensity that they're hearing at 66.6 decibels. Okay, so that is your L value. Okay, so you're looking at the loudness that they hear. So that is 66.6. So we want to find that I value, that intensity of sound.
But then why does it say concert venue can hear music at an intensity?
Because that's the total one that they can hear. So you're looking at the total loudness of it.
You should use their words.
Okay, so I'm going to plug in 66.6 for L. Okay, then I have 10 log of I over M is defined as 1. Okay, so I would have 66.6 is equal to 10 log of I, since I over 1 is just I. Okay, from here I want to get I by itself. So I'm going to divide both sides by 10. Okay, when I do that, I get 6.66 is equal to log of I. Now, how do I get I by itself?
We take the log of 6.66.
No. How do I get I by itself if it's within a logarithm? I have to bring in a base. What base do I have to bring in? Your common logarithm has a base of what? Your common logarithm has a base of 10.
Yes.
So you need to bring in base 10. Okay, so it cancels out here. So we have 10 raised to the 6.66 power is equal to I. Okay, so we can take 10, raise it to that power. Okay, and you'll get about, big number here, 4,570,800, and I'm just going to round to the whole number here, 882. Since you get 0.896 at the end there. Okay, so that would be your intensity at which the music is playing inside of that theater or wherever they were, that venue that they were at. Okay, that's why the people farther away can hear it. All right, then we're going to move on to solving some exponential equations using the common logarithm. Okay. So if both sides of an exponential equation cannot easily be written as powers of the same base, you can solve by taking the logarithm of each side. So before, when we were solving exponential equations like this, we were trying to get that same base, and then we could set those exponents equal to each other. Well, sometimes you can't find that exact number in order to set their bases the same. So what you can do is bring in a common logarithm. So For the following equations, our examples here, we want to round our values to the nearest 10,000th like we did on the front page. So first example here, we have 4 to the x power is equal to 19. Well, I can't change 4 and 19 to have the same base. So what I'm going to do is bring in a log to both sides. Okay, so I'm going to bring in that common logarithm to both sides. So rewriting this, I would end up with log of 4 raised to the x is equal to log of 19. Okay, so it's not canceling anything out when you bring these ones in. Okay, so we're just rewriting it as 2 logarithms. So whatever I do to one side, I do to the other. So now that it is a logarithm, I can use properties of logarithms that we learned previously. So if I have a power here, where does that power go? Out front. So I can bring this x out front here. So I would have x times the log of 4 is equal to the log of 19. Now I want to get x by itself, so what could I do to solve for just x? If I have x times log of 4.
Divide log of 4.
Divide log of 4. Okay, so I'm going to divide log of 4 on both sides here. Okay, so I do end up with x is equal to log of 19 over the log of 4. Now we can plug in that division in our calculator. Okay, we do have a common logarithm button. So here, first one I would type in, we take log of 19. I'm going to end my parenthesis. Divide that by the log, so press log again, of 4, and again end my parenthesis. Okay? So that I get my answer to be 2.12396, so 2.1240. Okay, that would be rounding to that nearest 10,000th. Questions? All right, do example 4. It's very similar to the one we just did. Okay, so example 4, do the same process there. What? You're done? Good job. All right, so in example 4, my first step here, I can't get the same base for both of those exponentials there. So I do want to bring in a log to both sides. Okay, so I would have log of 6 raised to the x power is equal to log of 42. Okay, again, I have an exponent, so my properties of logarithms say I can bring that out front. So I have x times log of 6 is equal to log of 42. Okay, divide both sides by log of 6. So we have x is equal to log of 42 over log of 6. And you can enter that into your calculator. And you should end up with x being equal to about 2.0860.
I got 1.73.
Did you end your parenthesis after 42?
No.
That's why. Okay, questions on example 4. So the same strategies that are used to solve exponential equations can be used to solve exponential inequalities as well. So instead of your equal sign, you do just have your inequality symbol. So in example 4, we're going to solve this the same way. I can't change those two bases. Okay, so I can't change those two bases to have a common base number. So what I'm going to do is bring in a log to both sides. Okay, so I have log of 3 raised to the 5y is less than log of 7 raised to the y minus 2. Now, since I have exponents, I can bring those exponents out front in both cases. So with my first one, I would have 5y times log of 3 is less than the quantity of y minus 2 times log of 7. Now I do write this as a quantity because you have to distribute this log of 7 to both of those terms. Okay, so I have to distribute that log of 7 to both of those terms. So here then, I would end up with 5y times log of 3 is less than y times the log of 7 minus 2 times the log of 7. Okay, so I distributed this log of 7 to both of these terms inside those parentheses there. Okay, because I'm trying to get y by itself. Now, if you notice, I have two y's right here. Okay, so I need to combine those somehow. So I'm going to subtract y times the log of 7 from both sides, because I want all my y's on one side of my equation. So I have 5y times the log of 3 minus y times the log of 7 is less than negative 2 log of 7. Okay, so now that I have my y's on the same side here, I'm going to factor out that y because I only want one y. So since both of them have a y in common, I can take that y value out so that I have 5 times the log of 3 minus the log of 7. Okay, and that's less than negative 2 log of 7. Okay, so now that I just have this one y, it's not in both of those now. To get that y value by itself, we're going to divide by that entire quantity. And that's on both sides of this equation. Okay, so I was just trying to get y by itself. Separated that out, factored it, then divided by that quantity on both sides. So now what you can do, we can enter this into our calculator. See if I can get it on here while you finish. So what I would do is put parentheses around your numerator. So I need a negative 2, then log of 7, end my parenthesis for the log, and end my parenthesis for the numerator. Okay? Then divide by this entire quantity. So I need to put a parenthesis around that entire quantity. And it would be 5 log of 3 minus log of 7. Okay, and then I can press equals. Okay, so you should get y is less than negative 1.0972. Now you do want to check to make sure that this actually works out. So since it's saying all the y values less than that negative 1.0972, you can plug in negative 2 since it is less than that value. Okay, so I'm going to use y is equal to negative 2 to check. So I'm going to plug it into my original up here. So that would be 3 to the 5th times negative 2 is less than 7 to the negative 2nd minus 2. So this is 3 to the negative 10th is less than 7 to the negative 4th. Okay, so you can plug each of those into your calculator. So if I plug in 3 raised to the negative 10th, okay, I get 4 zeros here, 1, 2, 3, 4, and then 1, 7 is less than, when I plug in 7 to the negative 4th, I get 0.0004. Okay, so this one right here is going to be greater than this. Okay, I have less zeros in front of it. Okay, so this is true. So that means my y value is less than negative 1.0972. Now, for some of these, I do have that study tip off to the left there. When you divide by a negative number, okay, when you divide by a negative number in an inequality, your sign has to flip. Okay, so if you divide by a negative number, your sign has to flip. Okay, questions?